Hi class, we're on section 11.4, complex vector spaces. This is basically a review pretty much of the entire textbook, just extended into complex spaces. So I'm not going to give a lot of examples here. We're really just going to run through some of the definitions and the theorems that we have, or review the ones that we have. And the examples that you'll see will be in the next video, the last video for the class. Okay, so again, we're really just extending the principles that we have developed already. Okay, so first let's talk about a complex vector space is. So again, a complex vector space is just an extension of a real vector space. So basically, it's a real vector space with complex values allowed. Okay, so remember in the video for 6.3 for complex eigenvalues, we did a review of complex numbers and how to find the modulus and how to write them with Euler's form and de Moivre's. So if you need a review again, just go back to that video. Okay. So the difference here is that the elements of our vectors, okay, and again, vectors is relative. Our vectors can be the standard vectors that we're used to. They can be functions if our vector space is a space full of functions. Our vectors can be matrices if our vector space we are working in is a space of matrices, right? So remember, vectors are not just the standard single line of numbers that, you know, your first introduction to vectors. Vectors can be anything that satisfies those conditions necessary for a vector space, which we're about to get into right now, right? So again, remember, vectors can be several different forms. They're not just, you know, a single vector in 3 space. They can represent functions. They can represent all kinds of different elements, okay? So our definition for a complex vector space is a set, which we'll call V, of vectors that together with the operations of addition and scalar multiplication satisfy the following axioms. Okay, first of all, we're going to need 3 vectors in order to show all these axioms, and we're going to need 2 scalars. Okay, so here u, v, and w in boldface are vectors as normal. K and M are scalars. In this case, our scalars are in the set of complex numbers. These are complex values. Now remember, a complex number is the overarching number system, right? It contains the reals, the imaginaries together. Okay, so these are complex numbers in the form of a plus bi. Okay, so the following axioms that we have are that if u and v are 2 vectors we have in our what we are hoping is a vector space, then me adding those 2 vectors will also still be in that vector space. Okay, so I am closed under addition. So the form of these vectors, if I add them together, they have the same type of form of things that are in this vector space. Okay, and as such, addition is commutative, right? U plus v is the same thing as v plus u. It doesn't matter which order I add them in, I should get out the same thing. Addition is also associative, so it doesn't matter which order I add things together in, they will be the same. So if I add v and w together first and then add u, it's the same thing as if I add u and v together and then add the w, right? So again, if these were regular numbers in the real number line system, which is a vector space, not complex, but it is a vector space, then 2 plus 3 plus 5 is the same as 5 plus 2 plus 3, right? So this holds true for complex vector spaces as well. And again, these can be matrices, they can be functions, they can be pretty much anything that has complex numbers inside of them. Okay, now that we're a complex vector space. This backwards E, if you don't remember, means there exists. Okay, so this means there exists a vector, a 0 vector inside of my set called the zero vector, okay, for V. So this exists for this set such that if I add this vector to any vector, it's the same as if I switch the order around, right? The commutative property of addition. So 0 plus something is the same as something plus 0, which will always get me out my original vector that I'm adding to the zero vector. Okay, and this is going to be true for every vector in my vector space, right? So this zero vector, we call this the additive identity, because when I add it to something, I get the same thing out. Okay, I get my additional thing. Okay, so the next one that we have is that for every vector in my vector space, there exists something called negative u, or the additive inverse. Okay, so the additive inverse is unique to this set of vectors, and if I take this additive inverse and I add it to my vector, it's the same thing as if I switch the order. Again, my associative property, or I'm sorry, commutative property of addition, I will get out this additive identity. Okay, so again, I'm trying to be very technical here because we've gone over this before. This is a review. Okay, we're just extending this idea, so I figure I can be a little more technical here. So my additive inverse, when I add it to a vector, will get out my additive identity. Okay, the additive identity is the zero vector. The additive inverse is this negative u, and again is not just negating all of the elements inside of that vector, right? It generally will have a very specific shape. A lot of times it is just negating all of those values inside of the vector. Okay, it really depends on how we define the addition and scalar multiplication. Okay, so for 6, if I have a complex scalar, right? So this looks something like a plus bi, and I have a vector in V, and again, now my vector here, even if we have just like a regular 3-space vector, right? So a vector, standard vector with 3 elements. If this vector, if the elements inside this vector are also complex, then I'm now multiplying something complex times a vector with complex elements. I will still get out something that looks like what my vectors are supposed to look like in V, right? So again, here I'm doing a lot of complex multiplication. So a complex scalar times, they could be real values, they could be complex values, right? So that's really what we're doing, is we're just extending this now to the complex number system, right? 7 is the same thing. If I multiply by a complex scalar across addition, then my vector space will exhibit the distributive property of scalars, right? So K will distribute to both vectors inside of my vector space. Okay. For 8, if I have 2 vectors being added, two scalars being added together, and I multiply that times the vector, then it's the same as me distributing not the scalar, but distributing the vector into my addition of scalars. Okay. And then 9 is the associative property for scalar multiplication. So m times u is the same as km times u. And for 10, 1 times u is going to give me out u. So this is the multiplicative identity, because when I multiply this by something, I get the same thing out, right? So additive identity, because when I add it to my vectors, I get my original vector out. When I multiply this times my vectors, I get my original vectors out, right? So additive identity, multiplicative identity, which is just 1. This is not unique. It is just a 1, okay? And this is my additive inverse, because what's the opposite or the inverse of addition is subtraction, right? So if I were to add something, 2 plus 3, right, I'm going to get 5. If I take 5 and subtract 3, I'll get back to 2. So this is just saying you're undoing your addition, okay, to get you out your zero vector, right? So again, this is a review from the real vector spaces. We're just, again, extending this into the complex set. So all these elements can have complex values inside of them, right? That's the only difference, okay? So when we went over the real vector space, we had a couple of things that we could then talk about, right? Because these axioms define how we define mathematics on a vector space. It tells me the type of additions I'm allowed to do, subtractions, multiplications. This defines my mathematics on my space. So now that I have my mathematics defined on a complex vector space, there are things that we are allowed to do now, right? So there's certain things that hold true, pretty much everything really, from the real vector spaces to the complex vector spaces. Things like additive identities, linear combinations, right? A linear combination is formed from 7 and 8, okay? So, really more like 8. Well, both of these really, okay? So now that we have these kinds of properties and the idea that we can change the order that we add things, so these things mixed with each other allows me to form linear combinations now, okay? Because I define what addition is, define what scalar multiplication is, and I define that it doesn't matter which order I add things in or which order I put them in, it's always going to be the same. So now that I've defined these things, I can use them to describe and come up with different rules for my space, right? So some of the rules that hold true are, okay, so things that hold true for complex vector spaces from the real vector space are the larger ideas, right? I can't get into everything because it's pretty much everything, right? So things like linear combinations, right? So these are derived from those axioms that we have. The idea of linear independence, which is based off of this idea of linear combinations, okay? Span, which is based off of linear independence, okay? Basis and subspaces, right? So these larger ideas and all the things that come with them hold true for complex vector spaces because of those 10 axioms that we had, okay? So the way that we find linear combinations, independent, span, basis, subspaces in real vector spaces, it all works the same for complex vector spaces, right? The only difference is that you just have to watch out for multiplying two i's together, right? Because then it turns to -1. So, you know, you just use the same math that you have for complex numbers, but all of that now extends to these ideas, right? So after we talked about, after we build axioms and we can build a vector space, the next thing that we want to talk about, the next extension to a vector space that's very important, was we started to talk about the dot product. And once we talked about the dot product, we learned that the dot product was just a very, very specific form of a bigger idea called an inner product, okay? And then we learned that if your vector space has a dot product, we call it an inner product space. So if we have a complex vector space that has an inner product defined on it, that is called complex inner product space. So now we're going to talk about inner products on these complex vector spaces. Okay, so now things will get a little bit different. The rules will remain basically the same. The only difference is that now, because remember, a complex inner product is a function that is defined on your complex vector space, or on your vector space, I should say, right? So we had inner products that were the dot product. We had the functions that were integrals. We had functions that were weighted dot products. We had several different types of inner products that we saw. So here we're not going to go over an extensive list of the different possibilities, because again, as long as the function you're using satisfies those 4 conditions, which we'll review right now, you can call yourself an inner product. Okay, so again, now that we have a function that is going to have some math involved, obviously, right, some calculations, we have to keep in mind that we are in a complex space, so we have to worry about things like conjugates. Okay, so there's really only one rule that's going to change, and that's the first rule. So we'll see that, and it's not necessarily that it changes, it's just that it has a conjugate in it. The other rules are identical for a complex inner product space. So our definition is, so we're going to need 3 vectors. So remember what an inner product is, right? The function takes 2 vectors from your vector space and it multiplies them according to some rule, right? Depending on what kind of vectors it is you're working with. And it gives you out a scalar, right? So what we're going to do is we're going to take 2 vectors, we're going to multiply them according to our function, and it will give us out not a real value, not a real scalar, but a complex scalar. So remember, complex is the overarching number system, so it could be a real number, it could be an imaginary number, or it could be a mixture, which is a complex number, right? So we're going to need 3 vectors, u, v, and w, that's inside of my complex vector space. Okay. And then I am going to need 1 scalar, which is a complex number. So we'll just call it C. I know we're using K a lot, so or R's and S's. We'll just use C for now. Okay. So an inner product on V is a function denoted by these 2 brackets. Okay, for you physics people, a lot of times I call these the brackets, right? From V to V, right? So something from V times something else from V, and will give you out a scalar, right? Your domain and your range that satisfies the following conditions, right? So the first one is that the inner product between U and V is going to be, this should be VU. Apologies, I'll fix that in the write-up. So these should be backwards, but it should be the conjugate, the complex conjugate of VU. Okay, so this should be reversed. It should be UV. So remember, the standard definition is UV equals VU. So the only difference here, it's still VU, but it is the conjugate of VU. So again, make note, please fix this. I will write it, I'll fix it in the write-up. It's hopefully the only error that I did not catch. Okay, U plus V, inner product W, is going to be, again, the same exact rule. I get to distribute this into 2 different inner products, U and W plus V and W. Okay, no conjugates here. The rest of these rules are identical to the regular inner product space. This is the only one that has a conjugate on it. Okay, so here, if I have a scalar times U, inner product V, I can pull that scalar out and inner product U and V. For 4, the inner product of a vector with itself is always positive or 0, and it's the only way it can be 0 is if the inner product with itself is 0, and the only way for that to happen is if U is the 0 vector. Okay, so these are exact same definitions from before, again, except for one where this is still switched. Okay, I just didn't switch it here, but it's a complex conjugate, right? So a complex vector space with an inner product defined on it is called a complex inner product space, or a unitary space. Okay, so this is not a very common term, but the term unitary is. We're going to talk about unitary elements in the next video. Okay, so just know that unitary is going to refer to complex inner products, right? So a note, okay, typically UV does not equal VU in a complex inner product space. So remember, for a standard real inner product space, that first definition I have is that we can reverse the order. Okay, the associative property of real inner products. In a complex inner product, you have to switch it and take the conjugate of the entire thing. It is generally not true that UV is the same as inner product VU. Okay, so you got to watch out for that. That's, again, the only difference from the first one. It does not generally hold true. Sometimes it does, special cases, right, but not typically. So a common complex inner product is the complex dot product, right? So again, the common real inner product, or Euclidean inner is the Euclidean inner product. So in the complex space, there's a complex dot product that is commonly used, just like we use the dot product a lot. That's why we had an entire section kind of dedicated to it before we extended it to the general inner product space, right? So just like the Euclidean dot product is important, the complex dot product is equally important for complex inner product spaces. So the definition of a complex dot product is very, very similar. U dot V, okay, is, so for the real space, we had U transpose V, right? So if I had two vectors U and 1 times V, I would just take U from a column vector and turn it to a row vector and multiply it times the column vector, and then, you know, the elements multiply. Here, it's the same thing. I'm going to get U transpose, but the second vector you have to conjugate, okay? So I'm going to get U transpose times V conjugate, right? So here, I'm going to take that U column vector, and I'm going to turn it into a row vector. This U, the secondary vector, is still a column vector, but you have to conjugate all of its imaginary elements in order to do your complex dot product. And that is why this is UV equals VU, right? Switching the order and then taking the complex conjugate, okay? So I'm going to have my U's are going to be the same, but all of my V elements, right, the elements from my second vector, are all going to be complex conjugates, right? And if I take U dot product with itself, it's going to have the same exact formula, right? So it's not U1 times U1, it is now U1 times the complex conjugate of U1, and so forth, right? So this is going to give me U1 squared. This is not absolute value here, you guys, okay? We are talking about complex numbers, right? So this is not the absolute value of U being squared. This is the modulus, okay? These are complex numbers, so these are the moduli of each complex product you're finding here. And that's going to be 0 or larger, obviously, because everything here is squared, right? So remember, the modulus of UI is you're squaring each element. A sub I, B sub I, because each U has an A and a B term, and you're squaring them and adding them together and then taking that square root. So again, if you're like, what the hell are you talking about? Go back to that 6.3 video and just review the geometry that we had there. Remember, a complex number is a vector in and of itself. Each one is a vector. And so the length of that vector, of that complex number, is given by the modulus. Okay, so that's what's going on here. You're finding the modulus of each of these. And if you're squaring these modulus, then you're pretty much just getting rid of this square root symbol, right? So the modulus of UI squared is just going to be the square of the terms, okay? So remember, UI is the modulus for UI. So each UI is A sub I plus B sub I times the imaginary I on the B term. These little sub i's are just the index for the U that you're talking about, okay? All right, so let's get into another theorem now that we've kind of discussed some of the standards for the complex dot product, okay? So the next one is, again, let's have 3 vectors in V. So really what we're going to do here, just as a heads up, is these are properties of the complex inner product. These are not the conditions to be a complex inner product. So remember, this is the definition of a complex inner product. Okay, if you want to have a complex inner product, you have to satisfy these 4 conditions. Again, this should be VU, not UV. Okay, so what we're going to go over now is the properties that result from a complex inner product. Okay, so the first thing that is always going to be true because of those 4 properties we have from the definition is, you know, so same setup, okay? The first one is that the complex inner product of that 0 vector, that additive identity with a vector is going to be the same as switching that order around, okay? Which is always going to give you out just 0, right? So remember, you get out a scalar from these things, right? And so maybe you're saying, well, shouldn't this be complex conjugated? Yeah, sure, why not? It doesn't matter. There's a 0 vector here. You're going to get 0 no matter what anyways, okay? So the next one is that u and v plus w is going to be uv plus uw. So now we're just showing the distribution from the other side, okay? Because the definition showed the distribution of u plus v with w. So you can also distribute from the other side. That's also going to hold true, okay? So u and cv. So remember, this is the side, the v side is the one that ends up getting complex conjugated. So if my c is with the u, it just gets pulled out. Okay, it just gets pulled out. But if it's with the v, especially since this is the side that generally is going to have the complex conjugate, again, this is just for the complex dot product. Even if I have a different complex inner product, it's still going to end up being the same. What's going to happen is when I pull out my c will need to be conjugated, okay? If it is with the v, okay? Not when it's with the u, only when it's with the v, with the second vector. All right? So now let's go over some of the formulas that we're used to, right? So let u be a vector in v, where v is a complex inner product space. Then we can talk about the norm of u, which is defined as norm of u, or the square root of the inner product of u with itself, which can also be written as inner product of u with u to the 1/2 power. Okay, so some textbooks like to use this. I'm pretty sure our textbook uses this more often or not. But if you see this, don't get confused. This is not some special thing. It's just the power. Okay. The distance from u to v. Distance from u to v is the norm of v minus u. And the next theorem that we have is, again, let's say we have two vectors in v, where v is a complex inner product space. Apologies, guys, we're not going to use this w vector. I must just copy and paste it because we've had to write this so many times. But for this one, we only need two vectors to show the properties that we have. Okay, so this is really just a list of some of the more common ones that you guys said you're familiar with. One being that the norm of u is positive, and the only way it's going to be 0 is if u is the 0 vector. Okay. The next one is if I have the norm of c times u, I can pull out the absolute value of c and multiply that times the norm of u, right? So it's a constant term across the whole, each element of the vector, so I can just pull it out and do my norm here. The Cauchy-Schwarz inequality is that the absolute value of the inner product between u and v is going to be less than or equal to the norm of u times the norm of v. And the norm of u plus v is going to be less than or equal to the norm of u plus the norm of v, right? That's the triangle inequality. And the last thing that we have is the properties of complex inner products. So again, we're just going to repeat the same things that we have for real inner products. We're just extending these ideas to the complex space, right? So for a complex inner product, u and v are orthogonal if and only if the complex inner product between them is 0. So that's the same definition. How do we know if they're orthogonal to each other? If their inner product is 0. Okay, so again, that's a very important rule because this drives a lot of stuff, right? Like orthogonal sets, orthonormality, the Gram-Schmidt, projection, like lots of stuff, right? Which again holds true, right? So if this is true, then all of those other things that are built off of this are also going to be true, which is on this list I'm going to talk about, right? If my inner product is 0, then u squared plus v squared equals u plus v squared, right? So this is the Pythagorean theorem, and it's true when it's a right angle, okay, orthogonal vectors, okay? The definitions of orthonormal right? Orthonormal matrices, orthogonal sets, and orthonormal sets hold true as well. So I'll fix this little typo, okay? And the last one is that the concepts related to orthonormal, orthogonal set, and orthonormal sets also hold true. Again, things like projection, diagonalization, Gram-Schmidt, orthogonal sets being a basis, right, etc. All the things that come with this, which is a lot, right? These all hold true. So basically, everything from real vector spaces is exact same thing in complex vector spaces, especially with a complex inner product defined. It's just that some of the math is, well, I guess you would say it's harder because you have to take into consideration conjugates and complex values and things like that, right? So the next and last video that I'm going to make for you guys, which I hopefully can get done tonight if I have a lot of stuff I need to get done, will be on applying these kinds of things to an extent in the complex inner space. Okay, thanks.